Welcome to another one of my myth-busting sessions. Today we're going to look at the myths that surround engraving on wood. Let me get started right away and show you what I mean. I dare say that most of you at some stage have tried to engrave on wood like this. This happens to be acacia wood, but as you can see, it's not made up of one piece of acacia, it's made up of at least two pieces of acacia glued together. Well, quite often you can't overcome that problem because it's very rare, unless you've got your own wood shop and your own supply of raw material, that you can get solid blocks of acacia. But even if you could, look, within one solid block of acacia we go from white to dark brown, almost to black. Let's have a look what happens. With the lens that I've got in here, I was running that at 400mm a second and with 40% power on this 70-watt laser. Now, even this, you could see one of the problems. Look at the colour of the engraving here as opposed to the colour of the engraving here and here. Now, it just so happens that it doesn't show here too much because I just happen to have the line of the E coinciding with the split line in the wood. But look, we've got this black engraving here and it gradually gets lighter here and then it's quite light here, but it's even lighter over here. If I feel that, you'll find that there's a definite step between this and this colour, this piece of wood and this piece of wood. It's engraving deeper and darker. If you look carefully, you'll see around the outside here there's all sorts of brown crud stuck on the surface. We've got a halo, a slightly smoky halo all around these letters because I'm engraving them very deep. Let's decrease the power because most people think that colour and power go together. Okay, so I've now reduced the power to 20% as opposed to 40%. The crud around the outside here is significant. Here I've got less crud around the outside, although there is a small amount of it there, but look, I've exaggerated the difference between these two types of wood. It's not uniform. It's not a uniform colour. Why is that? All the settings are exactly the same as they were here, and I'm going to do another test. I've made a significant change to the file itself. This one, as you can see, is very 3D, deep engraving, and it's producing a lot of sticky crud around the outside. This one is still 3D, and just here, again, there still is a significant step just here between these two types of wood. Here, we've got no 3Dness at all. It's completely flat. We're not producing any of this sticky crud around the outside. I could increase the power back to what it was here. There's just a hint of 3Dness across there, so I think you'll agree that that is significantly better than any of these other things that you would normally see. Now, I've specially prepared this file to produce this result, and I will let you into the secret of what I've done here. But before I do that, what I need to do is to explain the background behind what we're trying to do here. You won't understand what I've done here and why I've done it unless I start from square one. There are hundreds of videos out there that encourage you to find out what the best engraving settings are on your machine by running one of these matrix tests. It's a change of power and a change of speed, producing different colours. This is a nice plain surface that you'll find everybody does the matrix test on. In the real world, you're not dealing with plain, simple wood. You're dealing with very complex pieces of wood like this. Now, the first thing that I'm going to say to you is there is no such thing as wood. What's that? Well, generically, that's wood. But wood is not a uniform material. Wood is composed of atoms. And atoms are used to build up molecules. So yes, there are probably lots of the atoms in that part, and that white part there that are all the same. But they're also made up or constructed or bonded together in different ways. So that that material there is actually a different material to this material here. Now, you might say, yeah, but it's still wood. That may be true. But the problem is what we're trying to do, we're trying to destroy this wood with light waves. The light waves that we use are a specific wavelength. And I don't want to get too deeply into it, but I did say that this material is made up of atoms which bond together to make up molecules. The molecules here are different to the molecules here, and here, and here, and here. This is a whole set of materials that are masquerading as wood. It's not one material. Let's start from square one. Atoms and molecules are busy doing this. They're vibrating. That's what the temperature of a material is. Its vibration rate. Now, if we can make the vibration rate faster, we can actually make the material hotter. Think about that for a minute. So heat is not something that we're putting into the material. We're converting light energy, which are waves, into kinetic energy as it hits the surface, and we're making these molecules vibrate faster. And as we make the molecules vibrate faster, they get hotter. Now, you might think that making things hotter burns them. Well, it doesn't really burn them. That's just an effect that you see. What's really happening is the molecules are shaking so fast when you add this light energy to them that they actually start flying apart. And if a molecule loses some of its atoms, it becomes a different material. But when we add energy to them with this light beam, we are making them vibrate at different rates because every molecule has got a sensitivity. Let me give you a silly example. Look, when you were a kid, you went to birthday parties, and I can guarantee that on the table at a birthday party you would find a jelly or a jello and a birthday cake. Now, if you were one of these naughty little boys and you grabbed hold of the edge of the table to make the jelly shake, you would have done that, and you could make the jelly shake. What happened to the cake? The cake didn't wobble because the cake is made of a different material. So we've got jelly here, which is a dark colour, and cake, which is a lighter colour, which is not vibrating as much as the jelly. The jelly is shaking a lot, and when the jelly shakes a lot, what happens is the molecular structure starts to break down, and some of the atoms that are in that molecular structure fly off, and they become something else. Fumes, all this crud around the outside here. Okay, so if you look here, you'll see that the crud around this dark area is much greater than the crud around the lighter area, because there's a different chemical reaction that's taking place when we vibrate these molecules. The faster we vibrate them, the hotter they get. But it's not heat that's causing the molecules to break down. It's the physical, mechanical, kinetic energy in the vibration which causes the bonding between the molecules to break down. So it's an interesting physics phenomena that we look as though we're burning this material, but we're not. We're shaking it to death. And each of these materials has got a different strength and will shake to death at a different amount of vibration. So different molecular structures in this thing called wood are accepting this light energy at different rates. Some accept it readily and burn deeper, some resist it and burn less deeply, and that's why you appear to get different colours. Now, I've started to overcome that problem here with what I've done to the text. We'll talk about that later, but again, we need to go through this process step by step. So you now understand that you've got a product which is not uniformly going to accept your laser beam. So, what is the point of that? You found that you might want to go for that colour, but that colour only applies to this wood. It doesn't apply to that wood, or that wood, or that wood, or that wood. The chances are, if I had to do this test over here, we'll probably find that there's virtually nothing taking place on this white wood. The one thing that I do enjoy as my retirement activity is trying to understand how this technology works, because there are so much, excuse my language, crap out there. People do not understand how this technology really works. Now, you'll find, again, hundreds of experts out there that will tell you how lenses work on laser machines. And here it is. This is exactly what they will tell you. You get your laser beam coming into the lens like this, and it focuses down to a focal point just there. A focal point is the point through which all the light rays pass. Just remember that. All the light rays pass. Which means that if I fire my laser beam at a piece of material and I get it spot on the focal point, then no matter how long I leave the laser beam on or what power I throw at the material, I shall always produce the same so-called spot size at that point there. It's the focal spot size that everybody talks about. Before we go looking back at engraving, you need to understand what you're going to engrave, because there is no such thing as a focal point as defined by the manufacturer. Let me just show you what I mean. For this test here, I've been using a rather strange lens that most of you will not have in your collection. If you have a collection of anything, most people have probably only got one lens that came with the machine, which is probably a 2-inch plano convex zinc selenide lens. Well, what I've got in here is a rather strange material called gallium arsenide. What we have here are two lenses. One that you'll be familiar with, which is this one, a zinc selenide lens, and then we've got this other thing here. On the one hand, you can see through this lens, you can see my finger behind here, okay? You can't see my finger behind this lens because it is completely black and opaque. This is one of the weird properties of light. The wavelength of light that we fire at our material doesn't see that as black. It's completely transparent. It's a lens that focuses the light just as well as this lens. I've got one of those gallium arsenide lenses in this machine. Okay, now it's being used the right way round, i.e. it's got its curved surface on the top and its flat surface on the bottom. It's not essential to be the right way round, but I just happen to be using it the right way round for this experiment. Now, the reason why I'm using a 2.5-inch lens for engraving is because it's basically soft, i.e. it should give a fairly gentle burning effect on the surface. Sadly, there is no such thing as an engraving lens. All lenses are cutting lenses. So we're engraving with a cutting lens. Doesn't make a lot of sense, does it? Because you only want to damage the surface with a lens when you engrave. You don't want to cut with it. The next problem we've got is, what is the focal distance of this lens? Well, we can find out where the focal point is, supposedly as specified by the manufacturer. I've taken the woolly end off a Q-tip here, and I'm going to use that as a very gentle way of probing the depth that the lens is sitting there inside here. And I've put a mark on there, as you can see, and we'll measure the depth of the lens inside the nozzle. The manufacturer says that the focal point for this lens is 63.5 millimeters below the face of the lens. And what we've just measured is our nozzle here at 53.5 0.9. So that means I should have an air gap underneath the nozzle of 9.6 millimeters. Okay. Now, before I went away on holiday just recently, I had a little bit of a Brazilian job done, and I managed to rescue some spatulas from the beauty salon. These just happen to be nice 1 millimeter thick pieces of simple birch. We're going to set the lens to, let's not worry about the 9.6. We're going to set it to 10 millimeter gap because this has got quite a wide focal range. So with full 70 watts on there, at 10 millimeters distance, let's just do a pulse. I've burnt a lovely mark on there, and it's gone right through to the underside. Now let's just move it along a little bit, and we'll change the focus to 11 millimeters. Let's go to 12 millimeters. Let's go down the other way. Let's go down to 9. And I think you can see we're now beginning to get a bit bigger. So let's try 13. Not a lot different. And look at the marks on the underneath. So because this is a fairly long focal length lens, we've got a range over which this spot size remains reasonably constant. Let me do something else now. I've got no idea how much time I gave each one of these dots. I just pressed the pulse button, beep. It could have been 10, 30, 50, 60 milliseconds. I've got no idea. But what I'm going to do now is control the amount of time that I'm putting into each one of those dots. The machine allows me to set, say, 10 milliseconds for a pulse. We've still got full power, but this time we've got the focus set at 8 millimeters, and I'm going to do a pulse. Whoa! Which is the correct focus? Because if all the light is passing through one small focal zone, why is that dot smaller than this dot? Because all the rays are passing through there or through there. They can't both be right. 12 millimeters. Before we go and examine all these burn marks under the microscope, what I'm going to do, I'm going to run the same test again, but this time I'm going to turn the lens over. At the moment, the lens is used what people would class as the correct way to use the lens, i.e. the beam is coming in from the convex side and going out of the flat side. I'm going to be flipping it over so that the beam comes into the flat side and goes out on the convex side. So let's just do that. Okay, so that's the lens flipped round. So we start off the same as we did before, and we'll set this to 8 millimeters. So there's a repeat set of results. If you haven't yet bothered to go back and look at the matrix test video that I recommended, then here's one of the simple tests that I carry out in that video, which I must show you now because it's important as we go forward. So what I want you to see is a nice black line that I'm going to draw across this piece of wood. I don't think anybody will doubt the fact that I've just drawn a black line. Have I put carbon on the inside of the wood that makes it look black? Let me surprise you. Let's break that open. It's pale brown. There's no black in there at all. That's just nicely scorched, vaporized wood. So where's the black coming from? Well, the black is coming from your eyes. You see that as black because you cannot see the brown. And you can't see the brown because there is no light getting into that cut that's reflecting out so that you can see that it's brown. Now, that's a very important physics phenomenon about light that you need to understand, because it is that principle that I'm going to use and exploit to produce this result as opposed to that result. But we've still got a long way to go before we get to the end of the story. So there are two things you now need to understand. First of all, our laser beam is not a beam of uniform light. There is an intensity distribution within this beam which looks something like this if I draw a graph across there. In other words, that is a measure of intensity. The higher that peak, the more intense the light is. And as you can see, the most intense light in our beam is at the centre of the beam. So the more intense the light, the faster we shall reach the fastest point where the molecules fly apart. So most material damage is done by the central part of the beam. Things get a little bit more complicated, and when we go into the office and use the microscope, I will explain what happens to this beam when it passes through this lens. As you imagine that a lens will take that shape there and will magnify it and make it look something like that at the focal point. That's not what happens. That pattern of distribution gets destroyed as we get closer and closer and closer to the focal point. Here's the dot that I produced with the 8mm gap. Okay, this is out of focus by 2mm. Basically, this is 2mm into the material, the supposed focal point. And what you can see around the outside here is a lot of charring, black. And it's very, very slightly, if you look carefully, you might be able to work out that it's very slightly conical. Okay, and then it drops down into this black hole that goes right through the material. But around the outside of this black, look, you can see we've got various shades of brown, various types of scorching. So here we can see the profile that I've just described to you, where we've got a very high central intensity which is doing damage quickly and producing a hole, and then that area around the outside of the central intensity which is still doing damage but it's not doing it as quickly. And then we've got this really outer part here which is scorching and not even removing metal, it's just colouring the material. 9mm, and you'll notice the size and the scorching. Then we get on to the 10mm, which is the supposed focal point. Now, whether it's an accident of fate because I pressed the button at a different speed, I can't really say. But if we look carefully here, you'll see that there is a diameter, a hole in the middle, less scorching around the outside, and I've got a scale here which enables me to roughly assess what the size of the hole is in the middle there. I would say that the bottom of the hole is about there and the top of the hole is about here. So that's nearly a 0.3mm diameter hole. Now here we go to 11mm, 12mm and 13mm. Now if we look carefully at 13mm, you'll see that it is, first of all, not very much browning around the outside. We've got a very distinct black hole here, which happens to be somewhere in the region of about 0.25. So that looks to be a better focal point than the focal point that the manufacturer specifies. So let's move away from my untimed pulses and go back to the timed pulses. Now the first thing you'll notice is it's much easier to see the black hole because we've only got a small amount of scorching around the outside. We've hardly got any marking at all. So what we've actually done by controlling the time is to filter out the lower intensity part of the beam, and all we're doing is allowing the high intensity central part of the beam to vaporize the material and produce a hole. So there's our 10mm compared to our 9mm, and that's getting smaller, which indicates that the focus is getting better. Well, 11, the hole size is getting even smaller than that one. To get what I would class as perfect focus, remember, we want all the rays that are going to do damage to that material to pass through the same spot. So we've got two types of damage there. We've got scorching around the outside, and we've got vaporization of the hole down the center. You see, like that one. Now we're getting a much better ratio of hole size to outer damage. What we want is a black hole. We don't want a brown halo around the outside. And as you can see, this one is a bigger hole, but it's got a smaller halo. So this one would actually be a better choice to produce a black hole. 17 is not bad. So 16 and 17 appear to be the focal point for the lens at 10 milliseconds. That's 7 millimeters beyond what the manufacturer claims the focal point to be. So a 16 or 17 millimeter air gap with a 10 millisecond pulse is the point where we're seeing most of the energy passing through the same spot. Now that spot size is nothing like the manufacturer claims. The manufacturer claims for this lens that probably the spot size is something in the region of about maybe 0.15. The point I'm making is you mustn't believe what the lens manufacturer tells you, because the lens manufacturer has designed his lens for a camera, a microscope, a telescope, anything that transmits an image. We're not transmitting images. We are trying to concentrate intensity, power, damage to the material. And there's a different focus called an intensity focus, which is sometimes significantly different to the optical focus which the manufacturer claims. And as you've just seen, we're 7 millimeters away from the optical focus here. This is with the lens the correct way round, remember. So if I put it the wrong way round, I should get, presumably, disastrous results. Well, here's our starting point with the lens the wrong way round. And that's already a much smaller black hole with a halo, but it's not a dark halo. 9, 10. At the nominal optical focal point, we seem to have a very good small hole in the center where we've got maximum power, but then we've got quite a largish light brown halo around the outside. 11 is even smaller. 12, 13, 14. So the ratio of burn to scorch is changing now. We've got very little in the way of scorching and a lot of evaporation. 15. Okay, that's getting very good. 16 is good. 17 is getting a little bit more halo ratio. 18 is gain. It's starting to gain a bigger ratio of halo around the outside. I would say 16 looks to be about the best ratio now. So this is nearly a clean black dot. So using the lens the wrong way round gets us a smaller hole and a smaller burn. Why would that be? It's the wrong way round, but it seems to be performing better. Here's the curved surface of our lens, the flat bottom surface is here. Here we've got a graph of the intensity of the light rays within this beam. As I mentioned to you before, the most intense rays are at the center. And so what I've drawn is different coloured rays for different intensities as we move away from the axis of the beam. Just to make it easy for you to see what's happening to the power or the intensity distribution within the beam when it passes through a lens. Because it doesn't finish up like this. Oh, what's going on here? Well, this is something called aberration. We don't have a single focal point, because with something called spherical geometry, and I'm afraid that's what all our lenses are manufactured with, spherical geometry, you get a problem, and that problem is something called aberration. Basically, it means this: when the light ray hits that surface, the rays from the outer part of the lens focus at a different point to those rays that are coming through the center of the lens. So let's take a look at the red rays, and you'll see the red rays are focusing down here somewhere. So there is no single focal point. This may be something that the manufacturer would call the optical focal point, but that's not what we're interested in. We do damage with red rays, and the red rays are focusing at a different point to the general optical focal point, which is why we found that we were getting a damage profile which was 5 or 6 millimeters beyond what the manufacturer said. If we take a look at this picture, what you can see is that we've got all these rays out here. Look, the greys, the pinks, the blues, right through here to maybe something like these dark greens. These rays are pretty useless. They've got so little power in them. In 10 milliseconds, they just can't do any burning. There's no effect that can take place with these outer rays. The only ones that are having an effect are the maybe yellow, orange and red rays. By the time the red rays pass through this central section here and start focusing, the outer rays, which are not very damaging anyway, are even less damaging. Their energy is dissipated over a large area, which means that they don't do much damage. Our central hole, which is being evaporated by these rays, and a little teeny weeny bit of some damage caused by these rays that are adjacent to it. Now, when I flip the lens over, this is what happened. We've still got our beam with its intensity pattern right through the centre, but this time the rays are being refracted in a completely different manner. Look, we get massive aberration because we've got the lens this way round. Now, aberration you would think is a bad thing, but in fact if you look carefully, what it's doing is causing all these low intensity rays to spread out even more. So we're getting a massive filtering effect of the power because we've turned the lens over. And what we're seeing just here, we've got the bit that we want to work with, which is being concentrated. All the rubbish is being spread out over an area such that it cannot do damage. It's still there, but it just cannot do damage because the intensity is not great enough. I hope that makes sense to you. There's a lot more to understanding how lenses work than this, but it just explains why we're getting different performance from the lens the wrong way round. Right, what I'm going to do now is I'm going to create a new page, and the page is a bitmap page, which is, I'm making it A4 at the moment, but the important thing about it is I've got a resolution of 254 ppi, pixels per inch. It's the same resolution as this image here. In other words, each one of these squares is a pixel, 0.1 of a millimetre square. Okay. So I've created a piece of black text that's actually got a resolution to it of 254 pixels per inch. Now you can't see the pixels there because it's a solid black mass. You would either engrave an image from a bitmap or you would engrave an image from an outline. Either way round, you would be scanning backwards and forwards across that image and producing this text with the beam switching on, off, on, off, on, off, on, off. But all the time it's on, it's continuously on, producing smoke and fumes and burn, putting energy into the wood. So as it comes across different types of wood, you've got the same amount of energy going in, but the effect on the wood is different. So we start off with a black image, which you've seen the result of. It produces smoke, it produces different colours, and you can't do anything about it. Regardless of how you play with the power and the speed, you'll still get exactly the same result. So that's not the correct strategy for constant colour engraving. The correct strategy for constant colour engraving is to produce a load of black dots that sit together. That way you've got blackness, not different shades of brown. So how do we get to that? Well, the first thing we do in Photoshop is to change the colour of this text. First of all, I'm going to highlight this text. And now I'm going to go into the swatch here. I'm going to change the colour from black to mid-grey. And mid-grey happens to be 128, 128, 128 and 128. So we've got red, green and blue all set to 128, and it produces this colour here, mid-grey. Why on earth have we done that? Your eyes are really very strange things. They fool you all the time. You can clearly see that that's a mixture of black and white as a checker pattern. But if you squint your eyes, you might be able to mix the black and the white together. 50% black and 50% white represents mid-grey. And that's the colour that we've got here. Now at the moment it's mid-grey, it's not a mixture of black and white. So we can convert that solid grey image to something that looks like that checker pattern. Image mode. Now at the moment it's a coloured image, it says RGB. Right, we'll turn it to grayscale to start with, and it asks me if I want to discard the colour information. Well, obviously I do, yes. And now I go back again and I'll set the image, this time the image mode, to bitmap. In other packages you may find it's called dithering. You can't do this in Lightburn or RDWorks. You've got to do this process in an image manipulation software, something like Photoshop or GIMP. We've already got the image set up here to 254 pixels per inch, which will give us a 0.1 pixel resolution. And now we're going to ask it to do a diffusion dither. OK. And there we go. It's dithered it. So it's no longer what you think it is. First of all, let me zoom out like this, and you'll see that we've got a mid-grey piece of text. If I zoom in, what you'll find is we've got 0.1 pixels like this. We've now got 50% black and 50% white. Okay, so it's not quite a checker pattern, but the principle is exactly the same. 50% white, 50% black, that your eye mixes and sends to your brain as mid-grey. But because mid-grey is not something that the laser can produce. All it can do is change these pixels into little pulses, dots. And that's what we've been trying to achieve. We've been trying to achieve a black dot that's 0.1 diameter so that we can produce a mixture of 0.1 black dots on a white background. Now, we can do slightly better than that because, first of all, the chances are you cannot produce 0.1 dots. But if you produce 0.15 dots, what you're going to do, you're still going to produce your black dot, but you're going to occlude some of the white because you're going to remove the white background if your dots are bigger than 0.1. And basically, that's the trick. So we're going to produce a load of black dots to create an impression of black when there's no black there at all. Okay, now what you see on the screen at the moment is a special pattern that I've developed for determining the size of my dots. Now this is a crucially important pattern for me when I do photo engraving. But it's going to be very useful for you here to do normal engraving because it enables you to determine the size of your dots with this pattern. It enables you to focus in on the best settings for engraving. Now what we've got along the top here is a series of dashes which we use primarily to start with to get the focus. We try and get these as thin as we possibly can to find the best focal point for the speed and the power and the material that we're using. It won't be the same for every speed, for every power and for every material. If you put them together, you've got to find the best combination to suit what you're using. Everything on this pattern is 0.1. These pixels are 0.1 square. These pixels are 0.1 square and the white spaces in between are 0.1 square pixels. They're white pixels as opposed to black pixels. If we have dots that are 0.2 diameter, then the 0.2 dots will touch at the centre of the 0.1 whites. And you will see no white. What you will see is a series of touching black dots. So you can easily tell the difference between a 0.1 and a 0.2 dot. Now with the lens that I've got in at the moment, we're probably expecting to see 0.2 dots. So we just want black holes that are 0.2 millimeter diameter. And this pattern will help us find the settings for that. We've already got better results by turning the lens over, using it the wrong way. We're filtering out all the rubbish, low power. We're concentrating just the high energy, the high intensity part of the beam to produce evaporation of a hole, a black hole. Now this test pattern will demonstrate clearly to you how fickle focus can be, how much it depends on power and speed. Okay, now blink and you'll miss this program, so watch carefully. Well, the first thing we're going to look at, the dashes, and we're going to see whether one of them is any thicker or thinner than the other. It seems as though that 12 millimeters might be the thinnest line, but on the other hand, when we look at the 14 millimeters, can you see the central line of dots is more pronounced? For this particular test, we're looking for the combination of the thinnest top line and the most pronounced single dots along the middle. It's not very dark. We can make it darker by two things. We can either reduce the speed, which will increase the exposure time, and I think that's the first move that we will make. And you can see a distinct difference now in the colour of the bottom line and the middle line, and look at the crispness of those black dots along the middle line. So it looks as though 14 is probably the best focus, but hey, we can't say that at the moment. We've got to try and find a slightly darker and better result. So we'll leave the speed at 300. We'll put the power up to 30%. Look how thick the top line is on this one. It gets slightly thinner here. We've got reasonable dots across the middle, and then all of a sudden we've got this super crisp set of data at the bottom here. Look, we've got really crisp black dots across the middle, and we mustn't take too much notice of the bottom line because that's for photo engraving. And it looks as though those parameters are good. We'll try 340 and see what happens. Not crisp. It's it's a bit of a soggy sound, that test. Listen again and try and compare the sounds. That sounded quite crisp. Let's try 12. Listen again. That was even crisper. And sure enough, that looks pretty damn good. We've got a thick line at the top there that gets thinner and thinner. So 12 millimeters is the correct gap, i.e. 2 millimeters beyond the manufacturer's focal point. And look at the crispness of the dots along here as compared to these two. I think we're going to test this at 300 millimeters a second and 40% power. Now remember, this is the wrong material. So we need to do this quick same test, 12 millimeters distance, 340 parameters on our acacia, because they may be different parameters. We'll set the origin there and we'll run a test just here, and we'll also run a test here over into the white so that we can see the difference. Now that sounded crisp. You could hear every pulse almost. And look how black it is. You can see even here it's starting to change colour because we've gone on to the white. We could fiddle with it a bit more and try and put a bit more power into it. Put the power up to 50%, but to try and counteract the fact that I'm going to get some depth into the cut this time, I think I'll put the speed up to 400. Let's see what happens. This white wood is a lot more difficult to engrave than the other woods. But hey, we've still got reasonable black across here, look. It's not terrible, so we may well be able to deal with this at those settings. But you can clearly see how difficult it is to engrave the white. There's very little colour change across these various other woods. Now, I might be able to get that a bit darker. At the moment, what I've done, I've set the line spacing on this to 0.2 because I think the dots that I'm going to produce are 0.2 or more. so I don't really want to overlap my dots. So let's run the same test across this interface here, and we'll see what happens to all these browns as we cross here. Well, apart from the white, that seems to be pretty insensitive to the chemical change of the wood, and that feels absolutely flat. There's no 3D-ness there at all. So maybe I'll change the line spacing to 0.15. Well, the change is more noticeable when I close up the line spacing. So I'm going to open up the line spacing a little bit more to 0.25. Something that I can now see on the edges of these letters is a sort of a bit of a zigzag. That means that I have not got the scanning offset on this machine set correctly. So with so many different machines in this workshop, I've got all sorts of different offsets set for different machines. Yeah, that looks clean. Now, if you're using light burn, there's a little interesting twist that you can do on this. You can even do it in RD Works, but it's a little bit more fiddly. The text up with an outline, but it still doesn't fix this problem of a different wood within the same wood. When you choose your butcher's block, try and make sure that you use something which has got different shades of brown on it and nothing seriously white like this, because this technique doesn't work obviously for that. Let's try one on this side, which scans across this interface between two types of wood. You'll notice that we've got no debris around this, and I'll explain why just to finish off on this session. So why isn't this, with the same 50-60% power, as bad as this? It's not deep and it's not mucky. But the first thing you've got to remember is we're not doing continuous engraving. What we're doing, we're producing a series of holes like this in the surface of the material. We're continuously switching the machine on and off and on and off. You can hear it. Now what that means is that here we've got material which is solid and it has to be evaporated. It produces fumes. You've seen the fumes coming up. But the thing is, in this instance, the fumes have only got one way to go. They can only go up. Like that. Now, when you're doing a cut, continuous engraving like that, right? The only way for the fumes to get out initially on the first line is this way. So as the cut goes that way, the only place for the fumes to go is out along the kerf. And they will blow out along the kerf and they will settle on the surface here. Okay, now as you get further and further into the cut, you've got two dimensions of fume movement. One, the fumes will tend to go this way, away from your cut, because hey, there's nothing there to stop it. It's like a cliff edge. So the fumes that you're producing are going both this way and that way, and they're just covering your job. Here the fumes can only go one way, which is upwards and away from the work, so they will never settle on the job if you've got cross flow of air. to blow it away. And that's why you don't get shitty, brown, sticky residue when you do the engraving the way that I've just shown you. Okay, just a couple of final notes. First of all, you could go to the opposite extreme and get a slightly darker burn and a more uniform burn if you use a compound lens, which is specifically used for photo engraving. This is designed to produce 0.1 dots, and it's great for doing this sort of work. The focal length is 21 millimeters, so it needs to be set approximately 11 millimeters up from the work, because there's 10 millimeters inside the nozzle. It's an 11 millimeter gap, and we'll run the same program that we've recently run. I've got the line spacing now set to 0.1 because this is the dot size that this lens can produce. We're still running at 400 millimeters a second and 30% power on this machine. So there we go, there's a nice contrast for you. Just the merest hint of some texture there. Here's the same program run across this white and this dark wood. This white wood just does not want to take any colour at all. It doesn't burn. You can't even put a black hole in it. It's almost like rock, even though it looks white and soft. If you want to try a compound lens like this, you can buy this lens assembly with the lenses in from Cloudray. Now, many machines that don't have this sort of lens tube can still use this compound lens system because the lenses themselves are buried down inside the nozzle itself. And so all you need is a lens tube that's got a 22 by 1 millimeter pitch thread in the end. There are many machines that come with a 16.3 diameter, I think, stem that goes up inside their lens tube. You can buy a 16.3 stem lens tube with an M22 thread on it, again from Cloudray. It's a special that's designed to allow people with the older style machines and small heads to use one of these type of engraving nozzles and lens assemblies. So this dark engraving opportunity is available to almost everyone. And just one final footnote: if you thought that working with acacia or birch was fairly difficult, I suggest you never touch this stuff, bamboo. Look, it's a mixture of all sorts of materials. You can never ever get good engraving on this material. It will always come out banded like this. If it's an effect you want, fine, but I'm just warning you. Thank you very much for your time. I will catch up with you in another session when we'll try and put to bed some more laser engraving myths and misunderstandings.